Hello and welcome, everyone. Thank you for joining us from all over the world today. My name is Rick Frage. I'm the Director of Sales at SFTec. Today, Dr. Girish will be presenting about the test methods for determination of characteristic of properties of fiber glass bars. For you who have been joining regularly to these webinars, you probably know who Dr. Girish is. So I apologize for the repetition, but I will reintroduce him again for the new people. So Dr. Girish, basically, he received his PhD in civil engineering from the University of Sherbrooke in Quebec, Canada, after basically doing his master's degree in technology, a master's of technology in earthquake engineering in India. He also basically received University Gold Medal in 2013 for the Bachelor of Technology project on strengthening of reinforced concrete columns with externally bonded fiber reinforced polymer from the University of Veer Surendra Sai University in India also. His research interest includes the behavior of structural concrete reinforced with fiber reinforced polymers, testing and characterization of fiber reinforced polymer material, and nonlinear finite element analysis of reinforced concrete structure. Dr. Girish is a senior structural researcher at SFTec. We are based in Montreal, Quebec, Canada. And he is also a MITAX postdoctoral fellow at the University of Sherbrooke in Canada. He has assisted in many past and ongoing concrete structural projects with SFTec, including but not limited to structural slabs, column retaining walls, electric chambers, bases for communication towers, and so on. So basically, he's the best person to learn from how universities like the University of Sherbrooke test these products and determine the properties of the bars. Dr. Girish, the mic is yours.
Okay. Thank you very much, Rick. Thank you very much, Rick, for the brief introduction. Now, starting with our presentation. So today's topic is the test method for determination of characteristics properties of fiber reinforced polymer bars. So through this presentation, I will give a brief overview of FRP bar and continue with the different test method in physical, mechanical, and durability properties. Before starting the main presentation, I want to give a brief overview of SFTec. So SFTec, our products are mostly designed in Canada and are manufactured in China by Shandong Safety Industry Co. Limited, and who are specialized in manufacturing of fiber reinforced polymer products. So we work with national and international engineering firms. We work with them through the design process and help them with the fiber reinforced polymer design standards, whether they are in Canada or in the US. We generally focus on parking facilities, water treatment plants, and retaining walls. So our main focus are generally on the glass fiber reinforced polymer bars and carbon step applications. So SFTec FRP bar is made from composite materials, fiberglass and carbon fiber, and in manufactured by a filtration process using a mix of recycled fibers, and the recycled fibers can be glass, basalt, or carbon, and resins like epoxy. And this the figure which is showing the microscopic view of the fiber reinforced polymer bar. So three different types of fiber reinforced polymer bars are available in the market nowadays. Those are carbon, aramide, and glass. And the stress strain curve plot shows how these fiber reinforced polymer bars are compared with the steel bar. So 2 points should be noted from this plot. First, the glass fiber reinforced polymer bar have lower strength compared to the order 2 fiber reinforced polymer bars. And the second, the strength of all the FRP bars are higher than the steel bar. However, their behavior is linearly elastic up to failure. So we can, at SFTec, we can produce different types of fiber reinforced polymer products depending on the project requirement. And some of the fiber reinforced polymer bars we produce are straight bars, spiral, stirrups for transverse reinforcement, bent bars, and glass fiber reinforced polymer shear connectors. So shear connectors are generally nowadays are used in the minings and tunnels. The glass fiber reinforced polymer bar is widely used due to its production cost and have better tensile strain compared to other fiber reinforced polymer bars. So some of the advantages of SFTec glass fiber reinforced polymer bar over the conventional steel bars are: it have longer service life because of its corrosion resistance, therefore improve durability in harsh environments such as construction near coastal area in North American cold climate. And the FRP bars have better resistance against corrosion compared to steel bar. And as I told earlier, the tensile strength of FRP bar are 2 to 3 times more than that of the steel bar. So, however, it have more tensile strength. FRP bars are lighter due to low density compared to steel bar, and due to corrosion resistance, FRP bar are good for harsh chemical environments as well. And it is neutral to electrical and magnetic disturbance, useful for the applications such as airport, military application, MRI rooms in hospitals. So some of the selected field application of SFTec fiber reinforced polymer bars we have already done in Canada. So glass fiber reinforced polymer reinforced concrete waffle flooring slab designed with SFTec GFRP bars, which was built last year in Halifax, Nova Scotia, and it can be used for slab on grades. It is a non-structural slab, so it is a one-to-one replacement and saved a lot of money compared to steel bar in terms of labor and transportation, because GFRP bars are lightweight. They are too much lightweight, so you can save a lot of money in the labor and transportation. So another project shows the cast on site precast sandwich panels, and they have used our glass fiber reinforced polymer bars in their project as reinforcement, and it was built in China. And the last project on the right is the retaining wall built for the city of Montreal. And the retaining wall is designed to dump snow with de-icing salt during the winter. And so they built this retaining wall with SFTec glass fiber reinforced polymer bar, so which provided resistance against the chemicals used in the de-icing salt. Now coming back to our main projects. So as we already know that the reinforced concrete structures have many practical applications. They are used in commercial buildings, emergency buildings such as hospitals, so bridge piers in highway, railway, and metro bridges and flyovers. And with the increase in the sales of car year by year, we will need more parking facilities and recreational areas. So at that time, we need to think about a good sustainable materials which can provide a better serviceability. So the corrosion of the conventional steel bar has been the problem in reinforced concrete structure, which reduces the serviceability limit of the concrete structure. And this corrosion of the steel bar can be seen in the highway bridges and parking buildings. So the problem of the corrosion of steel bars can be overcome by using fiber reinforced polymer bars due to the following characteristics. The fiber reinforced polymer bars have resistance against moisture, alkali effect, and chemical attack, which mostly depend on the selection of appropriate resin, manufacturing process, and application of protective coatings. So therefore, the glass fiber reinforced polymer bars have resistance against deterioration due to chloride ions and carbonation. And in addition to that, the fiber reinforced polymer bars are lightweight, non-conductive, and magnetic free. So the characteristics properties of fiber reinforced polymers are polymer bar are divided into three parts. Physical properties, which generally includes the cross-sectional area, fiber content, water absorption, Q ratio, glass transition temperature. And the second is the mechanical properties, which include tensile properties such as tensile strength, elastic modulus, tensile strain, bond strain, transverse and horizontal shear strength. And the last one is the durability properties, which test the long-term mechanical properties of the fiber reinforced polymer bar exposed to alkali environment. So all of these tests will be discussed one by one later in this presentation. So there are 3 standards available in North America which cover the specification for the fiber reinforced polymer bars. So CSA S807 and F.932. The first one is CSA S807 and the last one is the F.932. So they consider for all types of FRP bars, either my bar is made from glass, basalt, or carbon. So whereas the ASTM 7957 only cover the specification of glass fiber reinforced polymer bars, as you can read in the title also, they only cover for the glass fiber reinforced polymer bars. So but CSA S807 and ASTM 7957 are widely used standard for the characterizations of the FRP bars. So there are 2 different types of test method which are used. One for the quality control and another test are used for the qualification. So I will differentiate these 2 in the next slide. So the quality control, the manufacturer should have in place a standardized quality control program that include routine sampling, inspection, and testing of constituent materials and end products of fiber reinforced polymers. So documentation of test results and management of materials is very important for the manufacturer. And both CSA S807 and ASTM 7957 recommended testing of 5 random samples from each production lot, and the qualification tests are done by an independent laboratory for short and long-term performance of the fiber reinforced polymer products. Like for SFTec, University of Sherbrooke is doing the qualification test. So the qualification tests are conducted to ensure constituent quality and compliance with the standards and specification. So total number of 24 tests from 3 production lots of each bar size should be tested. So from one production lot, there will be 8 samples, and these are the recommendation of the CSA S807 and ASTM 7957. So the following properties should be determined for quality control. So this facility should be inside where the bar is manufacturing. So there they have to provide all these properties: fiber mass content, glass transition temperature, degree of cure, cross-sectional area, tensile properties, and the CSA S807 require an additional transverse shear strength. This should be determined for the quality control. And in case of the qualification test, the number of samples are 24 for 3 production lots, as I told you earlier. And in addition to the quality control test, the following tests are required: bond strength, water absorption to saturation, tensile properties of the band portion, alkali resistance with and without load, and the load is required by the CSA S807. The tensile properties at the cold temperature, horizontal shear strength, transverse coefficient of thermal expansion, and creep rupture. These are only required for the bar number 5 or 15 millimeter bar. These are the additional requirement by the CSA S807. So now coming to the physical properties. We'll go one by one: physical, mechanical, then durability. So to determine the physical properties of the FRP bars, the following properties should be tested. So now I will only consider the qualification point of view. I will not consider the quality control. I will tell you all the tests should be done according to the qualification of the FRP bars. So the following properties should be tested. The test method for the following property will be discussed one by one, starting with the fiber mass content. So the fiber mass content, the specimens were generally cut to 1 inch for fiber mass content. And tested in accordance to the ASTM D2584, which was released in 2018. And the instrument used in the test were muffle furnace, which are capable of maintaining 600 degrees Celsius temperature, and a desiccator to cool the specimen. The specimen were weighed with an analytical balance to 1 milligram precision. So as I told you earlier, a total of 8 samples from each production lot were tested, and the 1 inch fiber reinforced polymer samples are heated at 565 degrees Celsius until the carbonous material disappear, and then the remaining residue is cooled and baked. So the fiber content by weight percentage was calculated using the following equation, where W1 is the weight of the specimen and W2 is the weight of the residue in gram. So for example, for the SFTec glass fiber reinforced polymer bar number 4, the average fiber content was found to be 85.6%, and which was higher than the 70% requirement in both CSA S807 and ASTM T7957. The next physical property is the cross-sectional area, and the specimen generally were tested in accordance to the ASTM 72505 2021 and CSA S80612 for the cross-sectional area of the fiber reinforced polymer bar. So the instrument used in this test were cylinder and measuring scale, and the specimen were weighed with an analytical balance to 1 milligram precision. So again, 8 samples were from each production lot were tested, and each fiber reinforced polymer specimen were weighed with an analytical balance to 1 milligram precision, and it's land carefully with a measuring scale, and then the specimen were placed in a cylinder filled with water and weighed, and finally the cylinder was filled with water and weighed separately. So the cross-section area or the specific surface in millimeter square or square millimeter was calculated using this equation SS is equal to MS by D, divided by L. And in this case, where the SS is the cross-section area and D is the density of the specimen, which is calculated using this equation, and where 0.998 is the density of water at room temperature, and ms is the mass of the specimen, mw is the mass of the water in the cylinder, and msw is the mass of water and specimen in the cylinder, and L is the length of the specimen. So for the SFTec glass fiber reinforced polymer bar number 4, the average measure cross-sectional area was around 100, measured by 151 millimeter. The nominal was 129 millimeter. And this area was greater than the required CSA S807 and ASTM D7957. So the next test is the water absorption, and the FRP specimens were tested in accordance with the water absorption procedure 7.4 in the ASTM D570, which was re-approved in the 2018. And the instruments used in the test were drying oven capable of maintaining the required 50 degrees Celsius. A water container was used for absorption. The specimen were baked with an analytical balance to 1 milligram precision. So a total of for each production lot, 5 and 8 samples for water absorption for 24 hours and 2 saturations respectively were tested. So the specimen were initially dried in an oven for 24 hours and baked after cooling in a desiccator, and it was called the condition weight. So I will tell you what is the condition weight later. So after conditioning, the specimen were placed in the distilled water kept at 50 degrees Celsius in this chamber. So we place the bars inside this and put it in this chapter, which were regulated at 50 degrees Celsius. Then the first baking occurred after 24 hours, and then the specimen were immersed in water again, extracted and baked every alternative weeks until saturation. And saturation was confirmed when the increase in weight over the 3 consecutive measurements were less than 1%. So the water absorption at 24 hours or 2 saturations was calculated as increase in weight in percentage equal to the wet weight. Wet weight is either the weight of the bar after 24 hours or at saturation. So the condition weight, which I told you earlier, so we initially dried the sample before putting them into water. That weight is the condition weight divided by the condition weight. And for the SFTec glass fiber reinforced polymer bar number 4, the average measure water absorption at 24 hours and to saturation was equal to 0.1%, which was lower than the 0.25% requirement in both the Canadian and American code. And at to saturation, it was 0.26%, which was lower than the required values. The fiber reinforced specimens were for glass transition temperature were tested in accordance with the ASTM E1356, and the instrument used in the test were differential scanning calorimeter was used with aluminum pans, and the specimen were baked with an analytical balance. So here for each production lot, 8 samples should be tested, and the small size specimen were cut and placed in the heat chamber, which we can see in this figure. This is the heat chamber, and which was kept under a nitrogen flow during the scanning procedure, and a heating ratio of 20 degrees Celsius per minute was applied, and the value of glass transition temperature was taken at the mid height. From this graph, you can see that it was taken from the mid height at the transition phase. When there is a transition, so here we back the graph and we take the value here. So for SFTec glass fiber reinforced polymer bar number 4, it was found the average measured glass transition temperature was 139 degrees Celsius, so which was greater than requirement in CSA S807 and ASTM 7957. So the degree of cure is the same. We use the same specimen what we use for the glass transition temperature, but the method we use is in accordance with the ASTM E2160. So the instrument, as I told you earlier, the instrument used in this test were the same what we use for the glass transition temperature, and the same number of samples we are going to use. And the scan used in the degree of cure test method are same as the scans used for the determination of glass transition temperature. So the degree of cure was calculated according to this according to this equation, where dC is my degree of cure, St is the total heat of reaction for the sample, and H is the normalized heat of reaction. So the value for the SFTec glass fiber reinforced polymer bar number 4, it was around 100%, which was greater than required 95% in ASTM 7957 and CSA S807. So these were my physical properties. Now, so whenever we do the qualification test, we first do the physical property test, and when the physical property test pass, then we will go to the mechanical properties. If the physical properties are not passing, we should not be doing any mechanical properties. So first criteria is to passing of the physical properties. So now coming to the mechanical properties. So under mechanical properties, there are various tests should be done. Those are tensile properties. So when we do the tensile property test, we cover the 3 main properties of the fiber reinforced polymer bar. Those are tensile strain, and the modulus of elasticity. The other tests are transverse shear strength, which is required by the both ASTM 7957 and CSA S807. And the last one is the horizontal shear strength or interlaminar shear strength. We can also call it interlaminar shear strength. And this is only required by the Canadian code CSA S807. So the first test is the tensile properties of the fiber reinforced polymer specimens, and these are tested with the ASTM D7205. So generally the instrument required are Baldwin testing machine, or we can say the tensile testing machine, and LVDT. LVDT is required for recording the elongation or displacement. So similarly for the physical property, here we also need 8 samples for each production lot. So in the test procedure, first we have to prepare the sample by installation of the steel tube on the both sides of the fiber reinforced polymer bar using the expansive cement. And the specimen were then, after the specimen was prepared, we keep them for 3-4 days for curing. Then after that, the specimen were instrumented with 1 LVDT of 200 millimeter length to capture the specimen elongation during the test. And test was carried out using the Baldwin testing machine as shown in this figure. So the tensile load was applied until the failure occurred, and the applied load and the bar elongation were electronically recorded using a data acquisition system. So after my test, I got the data from the acquisition system. So how we are getting only the tensile load. We already know the area of the bar. So from the tensile load and area, we can calculate the tensile strength. So my FU is my tensile load in Newton, and A is the cross-sectional area in the square millimeter. And the tensile modulus of elasticity was calculated. And this, the figure which I am showing, this is the procedure used in the ASTM 7205, not as per the CSA S806. In that case, there is a different procedure. So here the tensile modulus of elasticity was calculated by fitting a straight line to the data using method of linear least square regression analysis, and the strain rate selected for fitting the lines was within the lower half of the stress strain curve. The starting point of the strain was 0.001, and the end point was of the strain begin from 0.006. And these points are according to the latest ASTM 7205/21. Previously, the end point was 0.003, but they have increased it to 0.006 now. And for the SFTec glass fiber reinforced polymer bar number 4, the average tensile force was found to be 186 kilonewton, and this was sufficiently higher than the ASTM D7957 96 kilonewton. And also the tensile stress was 1520 megapixel, which was greater than the CSA S807. And according to CSA S807, the fiber reinforced polymers bars are classified into 3 types of bars: grade 1, grade 2, grade 3, depending upon the modulus of elasticity. So if my tensile modulus is between 40 and 50, then it is called grade 1. 50 and 60, it is called grade 2. And above 60 or 60, it is called grade 3. So these bars come in the category of grade. So, and one more thing, it can be noted here, the glass fiber reinforced polymer bar is the tensile strength of the glass fiber reinforced polymer bar is more than 3 times greater than the tensile strength of the grade 60 steel bar. So the next test in this category is the transverse shear strength of the FRP specimen, which was conducted in accordance with the ASTM 7617. And the test apparatus, as shown in the figure, consists of two bar seats, two lower blades, and two guide machine from steel. And these parts were bolted together with two threaded rods, washers, and nuts, as shown in this figure. And the upper plate was kept loose. This plate was kept loose so that we can put the samples inside, and it was fitted just prior before starting the test. And similar for each production lot, we are going to test 8 samples. And the length of each specimen, irrespective of the bar size, was 225 millimeter or 9 inches. And the specimen was centered within the shear apparatus, resting against the bar seats and lower blades, and place the upper plate into the bar and center the apparatus in the MTS universal testing machine. So the displacement rate was selected as to produce failure within the 1 to 10 minutes, and force was applied uniformly without subjecting the specimen to impact. So this figure can show the failure of these bars in transverse shear. So after testing the samples in shear up to failure, the transverse shear strength was calculated using this equation. And in this equation, PS is the failure load in Newton, and A is the FRP bar area in square millimeter. And for our SFTec glass fiber reinforced polymer bar number 4, the average value was around 149 megapascal, and which was greater than the requirement in ASTM D7957. So the next mechanical property is the horizontal shear strength of FRP specimen, and which was tested according to ASTM D4475. And this test is only required by the CSA S807 for qualification test. So if you are following CSA S807 for the qualification test, then you have to do this test. So the test apparatus consists of loading nose and supports. So the loading nose was suitable steel rod with a groove in diameter of the rod machine in its lower end, like here you can see it. And the bottom support was adjustable to allow for testing at various span to diameter ratios. And the surface of the groove, this groove was free of any sharp edges. So here for each production lot, 8 samples were tested, and all the specimen were cut to 6 times the diameter of the tested FRP, the size of the diameter of the tested FRP bar. So the test specimen was placed at the center of the test apparatus, and the testing span, means this ratio, the testing span to this ratio was around, span to diameter ratio was 4:1, and load was applied at a specified displacement rate until the interlaminar degradation of the fiber reinforced polymer bar occur, as shown in this figure. You can see these are the interlaminar degradation of the bars. So the horizontal or interlaminar shear strength was calculated according to this equation, and this equation is an empirical equation based on the number of tests. So where S is the horizontal shear strength in megapascal, and P is the breaking load in Newton, and D is the diameter of the FRP bar in millimeter. And for SFTec number 4, SFTec glass fiber reinforced polymer number 4 bar, the average horizontal shear strength was 50 megapascal, which was greater than the CSA S807. So this test is only required by the Canadian code CSA S807. Now, coming to the durability properties of the FRP bar. So the durability properties is the test we do in the durability property is the same what we do in the mechanical properties. Just here we do for the alkali resistance. So alkali resistance means we do the tensile properties, those including the tensile strength, elastic modulus, tensile strength, same thing, but we keep them in the alkali solution for 3 months. After that, we do the test. And here 2 tests are required. One is required by both the code, which is the tensile properties, and the other is the horizontal shear strength in alkali solution, which is only required by the CSA S807. So the alkali resistance in this test, we follow in accordance with the ASTM 7705, and a total number of 8 samples from each production lot is tested. So total 3 production lots are tested. Therefore, total number of samples are 24. So the alkali resistance consists of two test tensile properties and horizontal shear strength. So the fiber reinforced polymer samples of length 120 times the diameter of the FRP bars are used for the tensile properties, and 6 times the diameter of the fiber reinforced polymer bar for horizontal shear strength are used. As I told in the mechanical properties, we use the same length here, and those are exposed to the alkali solution. So the alkali solution consists of 118.5 grams of calcium hydroxide, 0.9 gram of sodium hydroxide, and 4.2 gram of potassium hydroxide in 1 liter of water. So the exposed samples are kept in the solution for 3 months, and they are kept at a temperature of 60 degrees Celsius. And after the 3 months, the samples are removed and tested according to the mechanical properties guidance for the tensile properties. Like for the tensile property, we use the same ASTM 7205, and for the horizontal strength, we use the same code what we use in the mechanical properties. So generally what we see here, the how much strength they lose after the exposure to the alkali solution. So for the SFTec bar, it was found that the alkali resistance was around 98 in average. The average value was around 89%, and which was greater than the both CSA S807 and ASTM 7957. And here you can see the CSA code is more strict. It provides a very high value of 85%, whereas ASTM provides only 80%. So these are all the properties what we test for the qualification test. So finally, in conclusion, due to there are many advantages of the FRP bars as we see over the steel bars. So it can be used in many structures, and those structures which are in the more vulnerable area, like in the coastal areas, like in the Northern America cold climates, like bridge decks, slabs, sea walls, mining and tunneling. The SFTec glass fiber reinforced polymer bar have passed almost all the physical and mechanical properties required by both ASTM 7957 and CSA S807. So therefore, the SFTec bars can be considered in the new construction, and we are also doing a certification test now, which will be completed in November. So we are very soon going to release our certificate also for that. And finally, the effective use of the fiber reinforced polymer bar would significantly improve the service life of the structure in harsh environment, and while minimizing the maintenance cost. Why I'm saying it will minimize the maintenance cost, because in the first part you will save in the labor and transportation cost, and plus for the service it will not corrode, so the service life will increase, so the reparation period will also increase. So there are the various types of SFTec bars are available at the SFTec bars, and these are some of the design codes and guidelines. And recently they have released the ACI 440-22. So previously the ACI 440-15 was only the guidelines. It was not a code. It was not a standard, but now they have converted it to standard. Now you can follow the ACI 440-22 and you can design the buildings in a specific in their what they have specified. And CSA S80612 is already there. I think soon they are going to also release a new code, maybe next year or 24. So thank you for your kind attention. And if you have any query, just let me know. Thank you very much.